So now we're going to start the Bernoulli equation, which is likely an equation you guys have worked with in college physics or even high school physics. But here we're actually going to derive it. You'll find that it's actually quite restrictive as to when you can actually use it, so it is not generally applicable, but nonetheless, it's still a very useful equation. So we're going to consider, for this analysis, when we're going to derive it, and it's not to put you guys through the torture of seeing the derivation, but if you go through the derivation, you see what assumptions are required to make the Bernoulli equation too. So that way you only apply if you have knowledge of when it is appropriate or not appropriate to use the Bernoulli equation, you do not use it in a scenario where it is not applicable. You will get incorrect results and your design will be way off. So the first thing we're going to assume, we are going to consider steady and inviscid flow. And recall that steady flow means that it's not changing with time. So the partial derivative of any variable, pressure, temperature, velocity, vector, density, etc., is not changing in time. And inviscid simply means that there are no viscous stresses. So essentially what that means is that we can assume that there are only pressure and gravitational forces, i.e. weight, acting on a fluid particle or element. Okay, and so now to derive the Bernoulli equation, we are going to examine Newton's second law on a fluid element. Okay, and this fluid element, I have a sketch here. So we have a fluid element here, and it's just moving along with the flow. And we're going to derive an equation of motion for this particle that describes the forces as it moves along a streamline. So we are applying F equals ma to a chunk of fluid or a fluid element that we've tagged, and we're going to examine the forces and accelerations that basically act on that fluid element as it follows a streamline. Okay, and so here, actually this would be y. Fix that. So so here we're going to define a few things. First, we will show that s will be the distance along the streamline. And so it follows the streamline. So if we have a streamline here, Rs is the total. Our S direction is the arc that is following the streamline. So if we have a streamline going in this direction here, S is basically the position along the streamline, and then S hat points in the direction of flow along the streamline. So if S is just the distance along the streamline, S hat is the unit normal vector of the fluid element on the streamline. Okay, but also the streamlines are curved, so there is a normal direction, and we're going to define n hat as pointing towards the center of a circle that is fitted onto a streamline. Because if you guys remember from your calculus that basically any curved line you can fit a circle to the point, and the radius of that circle to the center is the radius of curvature. So here I call that r. Okay. And so r is the radius of r is the radius of curvature. Okay? So now the nice thing is that basically we have a steady flow. That means the streamlines are not changing with time, and we're just basically following the small fluid element around and basically analyzing the forces on it. And note, we do not need to worry about flow going across the streamlines. And why is that? And that's because V which is defined to be going along the streamline because the fluid element is following the streamline, because v dot n hat is 0. Okay, and so why is because s hat is defined to be in the direction of the flow. Okay, and so recall that a streamline is tangent to the flow. Okay, so if the streamline is tangent to the flow, that means it is perfectly following the flow. And that means that there is no component of v in the direction of n, therefore v dot n hat is 0. And if v dot n hat is 0, that means fluid does not cross the streamline. So there is no transfer of fluid in this direction here, because again it would be going across the streamlines, and that doesn't even make sense in terms of the concept of the streamlines. And furthermore, because basically s hat is the tangent vector of the flow, that means v dot s hat is nothing more than the velocity magnitude. Okay, so that's just a little aside that will help you understand. So now we're going to apply Newton's second law, F equals ma, on this fluid element, and analyze the forces that are required to basically keep it on that streamline and accelerate it and decelerate it to whatever the flow velocity is. Okay, so now we're going to do that. Now let's do F equals ma, and we're going to assume that the mass of this fluid element is constant. Okay, and when we're analyzing these forces, another way that you can think about it is you can think of this like a train, and the streamline is the track. And if you know how fast the train is going as a function of position along the track, and you know the curvature of the track, you can then backtrack and then analyze the forces acting on the train that are required to keep it on that track. And that's exactly what we're doing on the fluid element. Okay, so you can think of it like a train, and the streamline is the track, and we're just analyzing the forces to keep the train on the tracks. Okay. And basically, we're going to say how do the forces on this change to keep the fluid element on the streamline. And so to do this, we're doing F equals ma, so that naturally implies we should do a free body diagram. So we're going to consider, and you guys will start getting used to this as you get to the upper level classes, say heat transfer and things like that. But they start in this class. We're going to consider a differential element of width ds and thickness dn. Okay, and we're going to assume that density is constant. Okay, so that's another assumption that we're making. Okay, so not only is it steady and inviscid, but we are assuming that the density of the fluid is constant. Okay, and so here is the free body diagram. It's kind of a mess, but our fluid element is right here. And note above that we basically argued that there are only pressure forces and weight acting on it, and so we're assuming that G is going down, and we're defining a Z to be in the direction of G. So you can think of Z as an elevation. Okay, so in the free body diagram we have weight going straight down. And this here is a small fluid element. It is of width ds, so basically, that's the width of it along the streamline direction, and the thickness is dn. Okay, and the center of it is at point n and s. Okay, and so in addition to the weight acting down in the direction of gravity, we will have a pressure times an area pushing, basically pushing on this lower side here. We'll have a pressure times an area pushing on this side here, a pressure times an area here, and a pressure times an area here. And note this notation here with the vertical line and n minus dn over 2, this means it is the pressure acting at position, acting not at, basically not at point n, which is right here, but it is acting, a distance dn over 2 down, down from the center of the element. So here we do need to keep track of exactly where we are analyzing the forces. And so here, this point here is pressure times area at, that is really small, so I'm going to make that bigger, at point, that's PA, at S plus ds over 2. Okay. And because basically that is the pressure times the area, and the location is not S, but it is a distance ds over 2 away from the center point of the element. And then so on and so forth for basically that force there and this pressure force here. Okay? So now we're going to apply, we know all the forces on this. And this here is just a little triangle here. The normal direction is here, and we're assuming the streamline makes an angle theta to the horizontal, and you can do some basically trig magic, and you have a normal component of the weight going down here, and a streamwise component of the weight basically pointing backwards, and that little velocity triangle looks like this, and the right angle is right there. Okay, so now we will apply Newton's second law. And Newton's second law is not F equals ma, it is actually the time rate change of momentum is equal to the sum of the forces. So here we'll define P, which is the vector, momentum vector, which is just mass times the velocity. And Newton's second law states that dp dt, and p, and the vector p again is just mass times velocity, is the momentum. So here we'll be applying this along the streamline, and we will work with this for this fluid element here. So we have a nice free body diagram, and we just need to keep track of all the forces. And it is assumed that we know the flow field and we know what the velocity is as a function of position along the streamline. Okay, so we'll just start working through it and see what the mass says. Well, this is momentum, as I said before. We just take the time derivative of that because we need this term here. And the free body diagram gives us those forces. It gives us the forces that we need. So dp dt equals dmv dt, which is just momentum, and we're assuming that mass is constant, so we can basically yank that out of the time derivative, and we have m dv dt, which is an acceleration. But we do need to be very, very careful, okay? So we can't just go and say, yes, we have completed the dp dt term. We need to be very careful because the velocity in the streamline, the velocity is a function of position along the streamline, okay? But the fluid particle at, say, time 1 will be here, and at time 2, it'll move further down the streamline and then be over here. Okay, so really its position is a function of time. So we have that the position is a function of time. So, and the velocity is a function of position. So in reality, the velocity is a function of position, which is in turn a function of time. So you can see where this is going from Calc 1. That implies we need to do the chain rule on this. Okay? So we can't just do a straightforward time derivative on this because the velocity is a function of position and the position isn't a function of time. So we work with this a little bit. So we know that the velocity, I'm just defining it. I'm defining the velocity to be the velocity at the streamline, and its direction is s hat. This is a vector equation, so we do need to keep very careful tabs of the vector. Also, you could think of Vs as the velocity magnitude. Okay, because we know that the velocity is tangent to the streamline. So you could also think of Vs as the velocity magnitude. So we just take the time derivative, being careful about the chain rule. So we just take the time derivative of that, because we know what that is. And we start working through the chain rule. So we have ds dt times partial v times partial s vs. Okay, well, this ds dt is just the velocity along the streamline. So we keep working through it, and we get that dv dt equals, actually this should be not I hat, that should be s hat. Vs, a partial Vs, partial s, s hat. Okay, because for this term here, we took the derivative of Vs and assumed that s hat was constant. And then there's a second term that we need to add, and that is the basically Vs, we're assuming that's constant, times partial s hat a partial s. And I'm not going to prove it in this class, but the second term, ds hat, ds is just 1 over the radius of curvature times n hat. Okay? So we now know this. It's a bit of chain rule magic, but it does work out in your guys' dynamics class. You guys probably dealt with this quite a bit too. A very similar thing. Okay. So thus, we have that dv dt equals vs times dvs ds in the s hat direction plus vs squared in the r hat direction. And this here is basically really a centripetal acceleration as the fluid element goes around a curve. That it is nothing more than that. In fact, if we didn't have that term, there would be something wrong with our analysis. Now, there's a bit of a problem here, is that we are basically, we need to relate pressure at the center of our element to the pressure on each edge, because they are at slightly different points, and we need to relate the pressure at this point here to the pressure on this edge here, and we need to relate the pressure at this point here to the pressure on that edge here, and the same thing for this edge and the same thing for that edge. So because they're not at the same location, we can't just sum the pressure forces, because we'd have some P1 here, a P2 here, a P3 here, and a P4 here, and a pressure at the center of it. So how do we relate those? Well, so we need to relate those to the pressure at the center. And unfortunately, we're going to have to use your favorite series, and that is the Taylor series. Okay, and so for the Taylor series, if you're going to recall that, we have the variable at any position at plus minus some space over 2 I chose it to be in that way just because that matches what we have above, is equal to plus minus dx over 2 times the x derivative of that variable with respect to x. Okay, plus a bunch of other terms, and I'm going to call those HOT, which is shorthand for higher order terms. And so this is the higher order terms, and we can neglect those. And then also, if you do a more formal analysis, you can show that those actually go to 0, that you don't need to include them. And later on in class, when I derive the differential form of conservation of mass, I will show you an example of the higher order terms going to 0. But we're not quite ready for that yet, so we will do that kind of stuff later on. Okay, so then we can apply the Taylor series and find the pressure at the edges in relation to the center of the fluid element. So we know that the pressure times the area evaluated at the center plus basically plus ds over 2 or minus ds over 2 is equal to, we basically have the same thing here for psi, but instead of pressure, it's pressure times the area. And we have PA here. And so we basically replace psi with PA. And, and that shouldn't be plus ds over 2, that should just be S. And so that would be the pressure evaluated at point S plus or minus the distance, which is ds over 2. I'll go back up to the diagram. So the distance from here to here is ds over 2, and the distance from here to here is ds over 2, just in the reverse direction. So we have that plus minus partial pressure times the area, ds over s. Okay, and first we need to find what the area is. Well, that area is just the height, which is given by dn, times how long our fluid element is, which I'm just going to take L, basically how long it is into the page. Okay, I'm going to assume some distance L. Okay, so this area here is dn times L, and we're going to assume that the area anywhere is just dn times L. Okay, so basically that's constant. So you could actually pull that area out of the derivative if you really wanted to. Okay, so I just use nothing more than the Taylor series on pressure times the area in the streamline direction. Okay, so we can basically gather terms in this. And this p times a at s plus minus ds over 2 just becomes p times dn, which came from the area, plus minus ds times dn over 2 times dp ds. And again, this dn came from this area here, and basically all multiplied by L. Basically, there is an L in basically both these terms that's constant, so I can pull that out. Okay, so it's just some very straightforward algebra to go from here to here. Okay, and I do the same thing with the faces in the normal direction. So in the free body diagram, it would be basically this face here and this face here. Over here, this corresponds to these two faces over here that I have circled. Okay, so we work with those, and here it's almost the exact same thing. Got the same mistake again. I need to fix that. But here the area is ds, because we are working with the pressure forces on this face, and so the width here is basically a ds times the depth into the page. So you could consider a planar face, and the width is ds and the length is L. and we apply the Taylor series. And again, the area in the area is the same basically everywhere. So we have a ds times L here, and we do the same thing, and we get a similar formula, except for we have ds here instead of dn, and the pressure derivative is in the normal direction rather than in this rather than in the direction along the streamline. Okay, so that's really the main difference. Okay, so now we know how to deal with the pressure on the face. This looks horrible. I assure you, it's not going to be that horrible. But it looks horrible right now. It looks like we've taken a mess and made it into an even worse mess that involves partial derivatives, which are awful. Okay, so now we need to figure out what to do with the weight. So the weight acts straight down, and here we are actually, that's nice, but we should really determine what the weight is in the normal direction and in the direction along the streamline. Well, weight is just the weight of the fluid, so that's rho times g times the volume. We're assuming density is constant, so basically mass is just rho times v. When we work with conservation of mass more formally, we will have an actual technically it should be a triple integral to find this, but we're assuming that rho is constant, so it's just basically rho times volume, and so it just the volume of the element is just ds dn times the length. Okay, so this here is the volume. Okay, so now we break it into normal and streamwise components, and basically using the angle theta and some trigonometry. Okay, so the normal component of the weight, it acts down, and that's just rho g cosine theta times the derivative, and or the volume, I should say. And the streamwise in the streamwise direction, it's just this, and so that all works out. So now we know all the components. We just need to put everything together. So we put everything together, and we started with dp dt is equal to the sum of the forces. And we know what dp dt is. Because mass was constant, we could basically pull that out. So that's just mass times dv dt, which we computed to be this term here, plus the weights, plus all the pressure forces acting on the sides of the fluid element. Okay, and we know what this weight is here. That is basically rho g. That is basically this expression here, which I argued is up here. Note, I already got the minus signs right there, and we have the weight acting on the streamwise direction here, and the mass is nothing more than rho times the volume. Okay, so we now substitute in our Taylor series expressions for the pressure times the area at all these faces, and we start working through everything. Okay, so this implies that we get this big, long, nasty expression here. All I did was I just substituted in our expression for mass, our expressions for the weight, and the Taylor series results for pressure. So it looks like I took a nice simple equation here and exploded it into this gigantic god-for-awful mess. But it turns out that there are a lot of nice cancellations. First, you may notice that there is an L basically multiplying every single term. So we can cancel those out. And then also, notice we have a p times ds here and a minus p times ds here. Okay? And we have a p times d in here and a minus p times d in here. Okay? And so those cancel out, which is very nice. And also note, it's encouraging that that our arbitrary length of the fluid element into the page did not matter, because it just canceled out. So that made things really, really nice. Okay, so now we can work with this a little bit more. So I just cleaned this up a bit. I just got rid of the L's and these terms here. And so this expression basically simplifies into this. Basically, these two terms are equal, and so the dsdn over 2, you add another dsdn over 2 dp ds, and so you just get 1. And so basically this is the reduced equation here. But notice that every term is multiplied by the cross-sectional area of the control of the fluid element, and so those also cancel out. And so what we are left with after I remove everything is a vector equation. That looks like this. Okay. So this is our final vector equation, and so it's a vector equation. It has a component along the streamline and a component normal to the streamline. Okay, so I already sort of uncovered it a bit, but this is a vector equation, so I'm just going to collect terms for all the directions. And first, I will do the direction along this along the streamline. So that will be the s hat direction along the streamline. So if I look at this sort of master equation here that has both, that will include this term here, and this term here. Oops, I had the wrong term. It'll be this term here, and this term here. Sorry about that. So we then gather those terms, and this is exactly what we have here. So we have v dv ds minus g sine theta minus g sine theta, and and tell you what, do this. Missed the row. Okay, so we have rho vs. There should be a row here. Okay, so we have a row vs dvs ds minus rho g sine theta. That's a really bad rho g, Ryan. Minus rho g sine theta minus dp ds. So I'm going to do what's traditional, and I'm going to divide both sides by rho, which is where I made that little mistake. Okay, so we have this expression here after I divide both sides by rho. Okay, so this still doesn't look very useful. We have all these derivative terms of the velocity and the streamline, and this equation does turn into the Bernoulli equation, believe it or not. But so we need to work with it a little bit more. Okay, so I'm going to multiply both sides by ds. You can do that. It'll drive mathematicians nuts, but that's kind of fun. So we multiply both sides by ds. So we have v dvs minus g sine theta ds minus 1 over rho dp. So we still can't do much with this, but let's keep working with it a bit further, and we'll see how useful this gets. So if we further assume that density is constant, we can actually move density into this derivative here. And you just have to go with me on this here, that normally you want to pull things out of constant terms out of the derivative. Here we're intentionally putting it in the derivative. It'll become clear later on. So if rho is constant, then we can put this 1 over rho inside the derivative and get a dp over rho. Okay? And we can apply an identity here that basically v dv is equal to d 1/2 v squared. Okay, so you could sort of see that d 1/2 x squared, if you just basically do this, you would have x dx. Okay, and there's no when you work in fluid mechanics, you see this sort of derivative. You actually see that you see that trick quite a bit, and so we need to and so you just learn to see it after you get some experience. Okay, so and so now we've sort of simplified these two terms here by making an additional assumption that rho is constant. Okay, so now we've layered on yet another assumption for our analysis. So we basically use that, and what's nice here is we've turned this v dv term into a perfect derivative, and perfect derivatives are nice to work with. And we have turned this dp term, this 1 over rho dp term into, you guessed it, a perfect derivative, which again is nice to work with. And I'm going to reiterate that is only if the density is constant. But now we have a little bit of an issue, and what do we do with this term here? So what do we do about g sine theta ds? Well, let's just look at the geometry. And if you look at the geometry, you'll find that you have dz in this direction here. ds is along the streamline. And you'll have some dx here. We don't care what that is. So, and we know that theta is basically this direction here. And so dz, and so sine theta is just dz divided by the hypotenuse ds. Okay? So then here we have a sine theta ds, and we can multiply both sides by ds. And so then basically sine theta ds is nothing more than the change in the elevation. It is nothing more than the change in the elevation. Okay? Then if the gravity is constant, and for most engineering applications it is, again, if you work in astronomy and things like that, it may not be. Or if you're dealing with an enormous change in the elevation, it may not be either. Okay, but if gravity is constant, then we have, then we can say that g sine theta ds is just g dz, which we basically argued from up there. And if g is constant, we can put that inside of the derivative. And so we have d times the derivative of gravity times the elevation. Okay? Which you could kind of think of as a potential energy, but it's... okay? Then we basically use our result here. We've now worked with this term here, and we have perfect derivatives for that term here. So now you notice we have perfect derivatives for every single term. So I'm going to move everything to one side. So, or this is equivalent to d1/2 of v squared times dgz, or plus dgz plus dp over rho, and that's equal to 0. Or these are all perfect derivatives and they're added together. So I can actually combine these into one derivative, like this. And we have the derivative of 1/2 v squared plus gz plus p over rho is equal to 0. And this is really nice now, because this entire thing is a perfect derivative that is equal to 0. This is very, very, very easy to integrate, because basically all it's saying is that there is no change of this quantity here. So there's no change in 1/2 v squared plus gz plus p over rho. Okay, and so it's a perfect derivative. It is easy to integrate. And if you integrate it, it would be the absolute, it's technically a differential equation, but it is the most simple differential equation to integrate because it's just the derivative is equal to 0. Okay, so we work with that and we wind up with the fact that 1/2 v squared plus p over rho plus gz is equal to a constant, and I'm dropping the s here just because we understand now that that basically v is the velocity magnitude along the streamline. Okay, or you could say because it's constant, you could pick any two arbitrary states, and you could say that basically 1/2 of the velocity squared at state 1 is equal to a p1 over rho plus gz1 is equal to the same thing at state 2. Okay, and this here is the Bernoulli equation, which you guys have probably used quite a bit. So basically, this is how the Bernoulli equation is derived. Okay, sorry about that. Sometimes the iPad kind of freezes up. So you guys have used this before in high school and college physics, definitely. So, but here we very formally derived it, and it is valid. And so we basically layered 4 main assumptions needed to derive the Bernoulli equation. And it is valid if and only if 1, density is constant, and that's called incompressible flow. And we'll discuss more about incompressible flow later on. 2 is it's only along a streamline. You cannot use it across streamlines, only in very special cases, which I'm not going to discuss in this class. Those of you who may be aerospace engineers, you deal with that case a lot in aerodynamics. But in this class, we're not going to deal with those with an irrotational flow. So for this class, you can apply it only along a streamline. Is basically at 2 different streamlines, the Bernoulli constant will be different for different streamlines. So you could say if you had streamline 1 here and streamline 2 here, these would have different constants. For Bernoulli. Okay, so you can apply the Bernoulli equation on this one streamline at any point, and you can apply Bernoulli equation for the second streamline along any point along that streamline, but you cannot apply Bernoulli equation to basically connect these 2 points here. You cannot do it. Okay, it is only valid along a streamline. So if you want to connect 2 points, they have to be connected by the same streamline. Okay, and in addition to that, we assume that the flow is inviscid, Later on, when we discuss pipe flow, we will actually correct for that and then add the influence of viscosity, which causes pressure drop in pipes and things like that. And we assume that the flow is steady, meaning that the streamlines are not changing with time and the velocity is not accelerating, and the streamlines are not changing with time, basically. Okay, and I repeat, do not apply Bernoulli equation across streamlines. I know some of you will do it, and you will be docked massive points on homework for doing that, and quizzes. So do not apply Bernoulli equation between two different streamlines. It is not applicable for that. And then also, you cannot use it for a compressible flow. That is, if the velocity of the fluid starts to become close to the speed of sound. And so, first of all, that violates the constant density assumption, because you could think of, for a compressible flow, you could think of, say, if your fluid element was air, you could think of, as the pressure is changing as we follow the streamline, well, the density of the air is going to be, if the pressure is higher here than it is over here, the density of the air is going to be higher here than it is over here. And that at the very least violates the constant density assumption. And it turns out that even for air, which is a compressible fluid, and which basically means that you can squeeze air and its volume can change, but it turns out that if the Mach number of the flow is basically is greater than 0.3, you cannot use Bernoulli equation, and CS is the speed of sound, equals the sound speed. Okay. So again, do not apply Bernoulli equation for that for those kinds of flows. If it's unsteady, that is, the streamlines are changing as a function of time, and also if viscous effects are dominant. And as I said before, we will correct for this assumption later on in class. So now I'll go through an example, and here we have an example here where we have a pressurized tank containing some water, like this, and it is being used to drive a flow out to make a fountain. Okay, and so the height of the fountain is h, and the pressure in the tank is P1, and the ambient pressure, I'm going to call that atmospheric pressure, or PATM, and P1 is greater than the atmosphere. Than the atmospheric pressure. Okay, and so we have basically our pressurized tank just spurting out what's called a jet of water, or which is called a jet. And I will go over a jet now. So a jet is just is sort of a fluid that exits a pipe, channel, nozzle, diffuser, etc., into the ambient. Surroundings. Okay, so basically it just means the portion of fluid that has exited the pipe and is now in the atmosphere is now basically free to expand in the outside air. And I will note that if the flow is compressible, or if the flow is not compressible, that is, the density is constant, or there's a very small change in the density, the pressure in a free jet is approximately equal to the ambient pressure outside of the free jet. So here we just have a picture of a pipe. And so here inside, this is just, this could be your hose, and this could just be you holding the hose horizontally, and then the water goes shooting out. So as the water exits the nozzle from your hose, and it starts to interact with the air, that's called a jet. And it turns out that the pressure in the pressure in the water exiting the nozzle is almost equal. It is very, very close to the outside ambient pressure, at least for the purposes in this class. So we can assume, because this is a free jet, and we're assuming that it is, that density is constant and it's incompressible flow, things like that, we can assume that the pressure in this free jet is equal to the atmospheric pressure. Okay, and we will be dealing with, and then sort of, don't worry about it. We will be dealing with jets quite a bit, and so you will get used to this assumption. Okay, so now, and we are asked, with that tangent aside, we are asked to find the height of the water fountain and the exit velocity of the fluid at the exit. And note, in this problem, I don't give you any numbers, so I just basically show you, this is the first example where we can work through with letters until the very end. So here, because Bernoulli equation requires a lot of assumptions to use, we need to, I do make you guys list those. So in your homework, you must list the assumptions. Okay, that basically tells me that you actually understand the concepts and you are applying Bernoulli or whatever equation appropriately. So first, we will assume that the pressure is the pressure in the jet, which is the atmospheric pressure. Okay, and we will take that the atmospheric pressure is 0, or you could say 0 gauge pressure. Okay. Okay, and so we will assume that because it's a free jet, and we will assume that the flow is steady. Now, you may be sort of wondering why, well, this is a pressurized tank and it's going to push the water down and the water is going to go spraying out. So isn't the flow really unsteady because the surface level here is going to be moving down as time goes on? The answer is technically yes, but essentially these tanks have a very large cross-sectional area, and you could actually calculate that the downward motion of the water surface is going to be extremely small compared to the velocity leaving it. So we can still assume that it is steady flow. Okay, and again, that is an assumption that you will get used to as we move forward with this class. Okay, we'll assume that the flow is incompressible, which means constant rho. Okay, and we'll assume that viscous effects are negligible, and we'll assume that the tank area here is much larger than the exit of the pipe, and that basically justifies the very slow motion of this of the surface here. Okay, and we will and you will get used to that as you work more and more in this class. Okay. And again, I will just reiterate that a jet is the flow of the water after it leaves the pipe. Okay. And this here, we will actually, when we start working with conservation of mass, this last assumption, we will basically work with that, and I'll show you more formally that this is actually true. Okay, that basically this area here being much larger than this area here implies that the velocity of the fluid here at the very of the water at the very top of at the very top of the level is approximately 0. Okay, and then notice here this problem is defined such that the height of the water in the tank is equal to the height of the water leaving the exit. Okay, so now the solution is we need to follow a streamline and use the Bernoulli equation. So we've hit 3 of the assumptions needed to use Bernoulli. That is steady flow, that is constant rho, and that's negligible viscous effects. But we can only apply it along a streamline. So we need to basically choose a streamline and then follow it. Okay, and so you need to basically in your homework, I expect you to draw a streamline to show that you are following that streamline. And so we'll call the top of the fluid state 1. Okay, so we will follow a streamline and apply the Bernoulli equation. So with this, we have all 4 requirements for Bernoulli. And again, in your guys' homework, I expect you to show all of the relevant assumptions required to solve a problem. And if you're to use Bernoulli, you basically need to explicitly list that you have all 4 requirements satisfied for you to use Bernoulli. Okay, if you use Bernoulli without satisfying those requirements, you will lose points. Okay, so we use Bernoulli equation, and so we know that 1/2 V1 squared, which is at the top of the tank, plus GZ1 plus P1 over rho equals the same thing at some state 2, which I don't know where state 2 is. We actually got 2 of them, plus GZ2 plus P2 over rho. Okay, so to solve these problems, it is traditional to pick a datum. Here a nice datum to pick is basically, in a datum is just a line where we are going to measure the change of elevation. And so here I'm going to choose the datum to be at the top of the tank, and which is also the point where the water exits the where the water exits the channel. Okay, and so we have and so basically Z1, because it is at the datum, Z1 is 0. So again, I want you to show the full Bernoulli equation like this, and then cross out terms. Don't just remove terms. So that's 0, and that's and then specify, and then tell me why you are zeroing that term out. So and it's 0 because datum is at the top of the tank. Okay, and we argued that basically that V1 is small. And because of that, we can say that V1 squared is much less than 1. And so that's going to be much smaller than basically this term here or that term here. So we don't need to worry about it. Okay? So, and we don't know enough about, and we haven't picked a state 2 yet, so we can't simplify the right-hand side anymore yet. Okay? And the reason that I haven't picked yet is because basically we are asked to find 2 things. We are asked to find the velocity of the water leaving the pipe and the height of the fountain. So we can have a state 2 here and another state 2 here, and they're 2 different states. But along all of those, we have the same streamline that we can basically follow. Okay, and basically we just follow the streamline and the find the exit velocity. We use Bernoulli between this point here and this point here, and to find the height, we apply Bernoulli equation between this point here and this point here. Okay, so working with this, we have so we can apply this to we can apply this Bernoulli equation. I'm just going to work with it a little bit more. So we have P1 over rho is equal to P2 over rho plus GZ2 plus 1/2 V2 squared. Okay, and so we will apply this equation here that we reduced from Bernoulli to find both the exit velocity and the height of the fountain. Okay. So first, the exit velocity. So we have that P1 over rho, which is the tank pressure, in gauge pressure of the tank, is equal to P at the exit over state 2. So this would be state 2. 2 is at the pipe exit. Okay. Plus G, Z at the exit of the pipe, plus 1/2 V exit squared. Okay, that is Bernoulli. So, well, it's a free jet, so P exit equals PATM, which we're assuming that is 0 gauge pressure. And that's by assumption. Again, in your guys' homework, in your quizzes, I expect you to cross out these terms explicitly and tell me why you are crossing them out. Just don't go randomly setting things to 0, and do not go into go into your book or the notes and look for equations look for equations to apply. This class is about building the equations to analyze your system, not just looking them up. Okay, and so now if we go back to, I'm going to scroll back up. If we go back to the point 2, we are assuming for finding the exit velocity that point 2 is here, which is exactly on the datum. So with respect to the datum, the elevation is 0. Okay, so Z exit equals 0, and V exit is basically what we are trying to find. So you solve for V at the exit, and you find that V exit equals square root of 2 P1 over rho. Okay. Okay, so now we use it to find the exit. Now we can also use it to find the fountain height. Okay, so again, we have P1, and I'll call that state, and I'll call that state 2. P1 over rho equals P2 over rho plus G Z2 plus 1/2 V2 squared. Okay, well, let's think about it. So we have our pipe that is shooting out some water, and we are asked to find the height of that fountain. Okay, so, and this here is state 2. Well, what is the velocity of the fluid at the very top of the fountain? It has to be 0, because basically in our streamline, which I'll draw right here, it's basically stopping there because the flow is basically turning around and then going back down. So at the very top of the fountain, the velocity is 0. So V2 equals 0 at the top. So that goes away. Okay. And again, this is this here is the entire thing is the free jet. So P2 equals P ATM, which equals 0 because it's a free jet. So that term goes away, and Z2 and the top of the pipe was basically where our datum plane was. So Z2 is nothing more than the height. So Z2 is just the height. So now we have an equation that we can solve for the height, and we can solve for h. This implies that h, which is the height we are after, equals the tank pressure over rho g. Okay, and note for both of these equations here that P1 is the gauge pressure. Okay, so that is it for this video. We will work with the Bernoulli equation, or not the Bernoulli equation, F equals ma for a fluid element, a cross streamlines in the next video.